Welcome back to Statistics, everyone. It's Sunday, March 29th, and this is our second example on significance test. Today we're going to look at what's called a two-tailed test. A two-tailed test is one in which the alternative hypothesis has the form mu different than, mu not equal to a certain value, which we're calling mu zero here. And this is a little summary box in our text on page 401. The examples that we've done up to now have both been one-sided tests. We had a right tail test for the weight of young men in Farmville, and we had a left tail test for the tip percentages left by patrons who received a negative message about tomorrow's weather after their meal at a certain restaurant. Uh, in a two-sided test, we're simply asking whether the sample data give evidence that the mean is different than a given value. And the only difference that comes in there is that when computing the p-value, you have to take into account both tails of a normal distribution. So let's take a look and see how that works out. The example that I have is with body temperature. It's commonly assumed that the normal mean body temperature among humans is 98.6 degrees Fahrenheit. But is that really accurate? Uh, we took an SRS of 20 adults and measured their temperature using an oral thermometer, and the average among those 20 was 97.5 degrees Fahrenheit. So, is this strong evidence at the alpha equal 1% significance level that the mean adult body temperature is different than 98.6 degrees Fahrenheit? Uh, and we're asked to assume that sigma is 2.5 degrees. So, the uh, standard deviation of body temperature from individual to individual is assumed to be 2.5 degrees. So, what makes this a two sided test is the form of that question. We're not asking whether this is evidence that the mean body temperature is less than 98.6 or bigger than 98.6. We're simply asking whether the mean temperature is different than 98.6. And that is the essence of a two sided test. As I said, our previous examples were one sided because we were asking, is the mean weight bigger than 172? Or is the mean tip amount less than 20%? Now we're just asking, is the mean different than 98.6? And so that leads to a different form for the alternative hypothesis, and you see it here. Uh, the alternative hypothesis is that the mean is different than 98.6 degrees Fahrenheit, where mu here stands for the true average human body temperature among all human beings, right? And so that not equals is indicative of what's called a two-sided test or a two-tailed test. Uh, the null hypothesis is completely the same in all of these kind of problems. It's that no, the skeptic's position is no, the mean is indeed 98.6, just like we've heard all our lives. And so let's see how this third form of the alternative, this two-tailed alternative, plays through into the computation of the test statistic and the p-value and so on. So again, let's just list our assumptions here. Again, we'll assume that we have sample data from a simple random sample. Our population variable is body temperature, which we'll assume to have a normal distribution with an unknown mean, but a standard deviation of sigma equal 2.5, and that all came from the problem statement. Uh, our sample data is a sample of size n equal 20, and we found in that sample that the sample mean was 97.5. So again, on the face of it, the sample data do seem to support the alternative hypothesis that the population mean is different than 98.6. But that's not definitive, remember, because after all, this is only a sample of size n equal 2, and mu here refers to the mean of all human beings. So a skeptic could plausibly argue that, well, even though your sample data does seem to be different than 98.6, you only have a sample of size 20, and I contend, says the skeptic, that the true mean, if you could take the temperature of every human being on Earth, would turn out to be what the doctors say it is, 98.6. So the essence of a significance test is to take the skeptic seriously, use the sample data to see how plausible his argument is. So we begin by thinking about the sampling distribution of x bar. It's normal with a mean that's unknown, but it's the same as the population mean, the mean of individual temperatures. The standard deviation is the standard deviation in the population, or 2.5, divided by the square root of the sample size, which is 20 here. Our test statistic is the z-score for x bar, assuming that the null hypothesis is true. So assuming that the true mean is 98.6, and here we're taking the skeptic, seriously, at least for the sake of argument, that means that we can compute the z-score, right? Because that would be our x bar value minus the true mean, which from the null's hypothesis is 98.6, divided by the standard deviation of x bar. And that turns out to be minus 1.9677. So what we're saying here is that if the skeptic is right, if the true mean is indeed 98.6, then our sample data, our x bar value, is almost 2 standard deviations below the mean, below where we'd expect it to be. That's getting out there. It's not a huge amount, not like the 4 standard deviations we saw in our previous example, but it is a significant number. And so let's see how that plays out. In other words, we recognize this as looking like it might be strong evidence against the skeptic's view, but how strong? Well, that's again where we compute a p-value. And so again, just reminding you of what a p-value is, it's the probability, assuming that the null hypothesis is true, of all test statistics at least as extreme as ours, that is our minus 1.9677, against the null hypothesis and in favor of the alternative. Now, you can think of the null hypothesis as being represented by the middle of the standard normal distribution here. And it's standard normal again because we're talking about z-scores. But remember, the alternative hypothesis here was not that the true mean is less than the null value, but that it was just different than the null value. So yeah, it's true that z-scores that would be less than minus 1.9677 are evidence at least as strong as ours against the null and in favor of the alternative here. But because the alternative is two-sided, it's also true that z-values that are at least as far from the null value on the other side also count in favor of the alternative hypothesis. That is, if I had measured an x bar of, say, 101.6, then that would also be evidence in favor of mu not being 98.6. And so the p-value for a two-sided test is going to be computed from all the z-scores in both tails that are defined by the test statistic. So you're seeing that here in this picture. Z-values that are less than minus 1.967 are bigger than 1.9677. Both constitute evidence at least as extreme as ours against H0 and in favor of HA. And that's why it's called a two-tailed test. And then once you realize that, computing the p-value is not hard. In fact, you can just use the symmetry of the normal distribution here. A two-tailed test, you can just look at the probability in one tail and then multiply it by 2, which is what I've done here. So we have twice the probability that z is bigger than 1.9677. And now that would be this TI-84 command. And that turns out to be about 0.0491. So a 4.91% p-value. What can we get out of that? Well, remember, small p-values are evidence in favor of the alternative. 4.9% is fairly small, right? And so we have moderately strong evidence against the null hypothesis that the mean is 98.6 and in favor of the alternative that it's different than 98.6. Why do I use the word moderately here? Well, generally, p-values between 1 and 5% are thought to be moderately strong evidence in favor of the alternative. And so that's what we have here. Strong evidence is generally considered to be a p-value that's less than 1%. And we don't have that here. So at the 1% significance level, our p-value is actually bigger than the significance level. 4.9% is bigger than 1%. So at the 1% significance level, that's a strong, significance level. We would fail to reject H0. We just don't quite have enough evidence to reject the null hypothesis at the 1% significance level. But note, you could, if you change the significance level, if the significance level was 5%, then you just barely make it under the bar with a p-value of 4.9%. So at a 5% significance level, you would be able to reject the null hypothesis. So this brings up an important point, which is, whether you ultimately wind up rejecting the null hypothesis or not really depends on the significance level, that cutoff value, alpha, that says, how small does p have to be before you wind up rejecting H0. I think our problem told us to use alpha equal 1%, so there we can't reject H0. With the last three examples, those last three videos, we now have examples of all three of the variants of the basic idea of a significance test. So where we're going to be headed next is in removing some of the sort of unrealistic assumptions we've made, namely the assumption that all the variables we have to deal with are normally distributed, and also, the assumption that we have to know the standard deviation of our variables, because generally that's not the case. But we'll take a pause here and pick back up next week. Homework 30 is due Monday night at 11 o'clock, so don't let that slide. Let me know if you have questions or if you have other types of difficulties, internet difficulties or anything like that. Hope you're all staying well, and we will talk to you soon. Y'all take care.